In this video, we're going to go over a few important notes related to Coulomb's law and the equations that we arrived at the end of the last video. So just as a refresher, I have here the figure from the previous video where we were considering our Q1 and Q2 charges, as well as the two forms of the equation that we arrived at the end. So we were looking at our force sub 1, 2, which we said is the force on Q2 due to Q1. So the first point or note that we want to make is that the force on Q1 due to Q2, which we write as F sub 2, 1, is equal to negative F sub 1, 2. So our force on Q1 due to Q2 is in the opposite direction of the force on Q2 due to Q1. And the reason for that is because the unit vectors are in the opposite direction. And so we'll come back to another point on that. You might be thinking, well, what if one was an electron and one was positively charged? Wouldn't they be attracted to each other? And we're going to come back and make a note on that here in a second. The second point that we want to make is, as we were just sort of talking about, is that in general, like charges repel and unlike charges attract. So we need to sort of keep that in mind and maybe use that as a double check at the end once we've done our calculations to make sure everything makes sense. The third point is that the distance between the charged bodies must be large compared to the dimensions of the bodies. And so essentially what we're saying here is that we're considering these bodies to be point charges. The fourth point is that our charge Q1 and Q2 must be static, so these charges can't be moving around. Again, we're going to come back in later units and talk about currents and magnetic fields and electric fields and how all of these things relate. But for now, we're just considering static charges. 5 is that the signs of Q1 and Q2 need to be accounted for in these equations. And so this relates back to sort of our points 1 and 2, really our second one. So for instance, if we had an electron for Q1 and a positive charge for Q2, well, we'd have to put in, negative charge of the electron and then plus whatever our charge is on our positive charge. And we note that that's going to give us this additional negative sign. So for example, now our F sub 1, 2 would be going in this direction, and this would be in the opposite direction, so we'd have forces moving towards one another. So we need to be careful to account for the sign of the charge of both charges when we're using these equations. And then the sixth thing is not necessarily related directly to using this equation, but just in general, charges cannot be created or destroyed. So we can't just create a charge out of thin air and say, here it is at this point. And if they're moving towards each other or forcing each other certain ways, they're never going to destroy one of the charges. So one additional thing that we want to talk about in this video is here we have this simple case, the simplest case really, of just 2 point charges. So how do we handle this if we have more than 2 point charges? Well, what we can do is we can use the principle of superposition. So we can say for more than 2 point charges, we're going to use essentially the same equation, but we're going to use superposition and sort of consider, say we look at one charge and we're saying what is the overall effect on this one charge due to all of the other point charges that are close enough to sort of have a force applied on it. So for more than 2 point charges, we're using superposition, and what that's going to give us is the total force on a given point charge. So total force on a particular point charge. So it doesn't tell us the total force in the system, just on one particular point charge. And so let's say we want to know the force on some point charge, and then that's going to be equal to Q. So Q is going to be the charge of the point charge of interest divided by 4 pi epsilon naught, so that's our proportionality factor K, and then we're going to have a summation. And the summation is going to go from K equals 1 to capital N, and we're going to have the charge of our kth other point charge, the position vector of our charge of interest minus the position vector of our kth point charge, divided by the magnitude of that distance, which we had previously written as r minus r sub k, or rather position vector 1 minus position vector 2, raised to the power of 3. And so that's how we can kind of scale this up to deal with any number of point charges. And so again, our charge of interest is Q. So by charge of interest, I mean that's the charge that we're finding the net force on. Charge of interest is Q, and that's located by our position vector R. And then we have N other point charges with charges K sub Q and located by position vectors R sub K. So in the next video, we're going to talk about our electric field intensity, and then we'll finally look at an example and see how we actually put these equations to use.